All right, so Chapter 8, well, let's see, Lecture 35, Chapter 8, Section 3. Now we're going to focus a bit on our multiple bonds. Okay. So remember what I said back in Section 2. Hybrid equals sigma. Pure equals pi. Okay. So every bond, there's going to be some sigma element to it, because you always start with those hybrid orbitals, and then you tack on, double and triple bonds on top of that, and those double and triple bonds are our pi bonds, and they are going to be, just pure non-hybrid orbitals. Now let's explore some of what that means for our geometries. Once again, let's look at ethane and ethene. Okay, so C2H6 and C2H4. Okay, so here we have carbon bound to 3 hydrogens, bound to carbon, bound to 3 hydrogens. And down here we have carbon bound to 2 hydrogens and a double bond to another carbon bound to 2 hydrogens. Okay, so up here, each of these guys is sp3 hybridized. Down here in ethene, they are sp2 hybridized. Okay, and this bond in the middle is a sigma bond and a pi bond. Okay, now the interesting impact that this has on them is that this is free to rotate. Okay, if you look at ethane up here on the top, okay, each of those carbon atoms and its attendant hydrogens, they are free to spin willy-nilly any which way they want. Okay, because that single bond, all of the electrons are located in between the two carbons. Okay, so all electrons here, okay, they're in between them. They're on that internuclear axis. Okay, so if you spin it any which way you want, okay, that's not going to change the location of those electrons. Whereas that cannot be said of this ethene down here. Once again, let's look at it. Edge on, right? So we have our 2 hydrogens, okay. For this molecule, you have, your sigma bond in between, but you also have the pi bond above and below. What that means is that if you tried to rotate it, if you tried to spin either of these carbons, you would be pulling, you'd be pulling that pi bond apart. Okay, you'd be trying to separate the electrons in those orbitals. Okay, so there's no way to rotate it. Okay, which means that ethene is locked down. Okay, it can't rotate. That bond is fixed. Okay, so it really is a nice flat molecule like that. Whereas this is all wiggling and flopping all over the place, the ethane up top. Ethene is much more locked down. It's much more rigid. It's more locked in place. So that is something that multiple bonds do. Multiple bonds equal rigid molecule, or at least rigid at the location of the multiple bond. Okay. If you continue studying chemistry, if you go on to look at biochemistry, this has a big impact on fat molecules, for example. Okay, the more double bonds those fat molecules have, the more rigid they become. Whereas fewer double bonds means that those long fatty acid chains are looser and floppier, more tangledy. It has a lot of impact in a lot of places, actually. That's just one example. And you see the exact same effect, more exaggerated in ethine or acetylene. You might recall is C2H2. It is carbon triple bonded to carbon, right? So each of these carbons, only 2 electron domains, is sp hybridized. And then you have a pi bond above and below, and a second pi bond in front and behind. So it is doubly locked down. Okay, so very rigid, that bond. So pi bond equals no spin zone. Okay, a pi bond always locks down that section of a molecule, keeps things from rotating. All right. Now let's look at resonance. Resonance only shows up when you have pi bonds. You have to have a multiple bond in there somewhere. Okay, so only with pi bonds can you get resonance. Sigma bonds don't resonate. Those hybrid orbitals, there's no resonance there. So let's go ahead and look at one of the most famous examples of resonance, benzene. Okay, benzene is C6H6. Okay, that is, it's a ring of carbon atoms. Bound to hydrogen atoms. And then you have double bonds between half of the carbons, which means that each of these carbons is sp2 hybridized, and it has a free p orbital available to form that double bond. Okay. Notice that each one of these carbons is only participating in one double bond at a time. Okay. So double bond on one side versus single bond on the other. Okay. Now let's just look at, like 3 of the carbons. We'll put it on its side again. Okay. So that, so the double bond is formed between those p orbitals, which are going to stick up and down, above and below the plane of the ring. It's a nice flat ring. Now, the reason you get resonance is because, the carbon looks to either side and it says, I can mix with this guy on the left, or I can mix with this guy on the right. I don't have to choose. Okay? So it instead mixes, with both of them at the same time. Okay? So now, hopefully, this gives you a better picture of why resonance happens. Okay, it's not so much that, both pictures exist simultaneously. It's that these orbitals are overlapping and mixing. There's no reason why it can't, sort of spread itself out to both sides instead of just to one side. Okay? So when you look at the ring, okay, so if this straight flat line here is the ring, what you see is this sort of cloud of electrons. Okay, I'm trying to, above and below. Okay, and these are your resonant pi bonds. Okay, above the ring and below the ring at the same time, and in between all the carbon atoms at once. Okay. So down here at the bottom, I'm drawing the simpler picture of that benzene ring. Okay, where you have the double bonds. They can either be between 1, 2, 3, and 4, 5, and 6, or they can be between 2 and 3, 4 and 5, 6 and 1. Right. Well, what actually happens is this picture I've drawn here, where you have the pi bonds are sort of smeared around the entire ring all the time. Okay, that's why the 2 resonance pictures exist together, is because those 2 pictures are each kind of a lie. Instead, what you get is this mixing taking place above and below. And that's true regardless of what sort of resonance you're talking about. Let's look at acetate, C2H3O2 minus. Okay, it's H3CCOO. Okay. Now, I mean, all we really care about is the resonance on the right-hand side of that molecule. And it is the exact same sort of thing. Okay, so we draw it like this. Okay, this carbon has that p orbital. Each oxygen also has a p orbital available. Okay, so why not mix with both of them at the same time? So when you sort of look at it, from the side, you'll see, a sort of smear of electrons above and below. It's not quite as pretty. It doesn't make that nice ring above and below like you get with benzene, but you still get that resonance. Okay, as the p orbitals on the carbon and the two oxygens mix all at the same time, making the pi bond that is what is known as delocalized, okay? Because it's no longer confined to a specific location. So that is a delocalized pi bond is what we're looking at. And this doesn't just have to be, carbon. You could also get it with, say, nitrite. So nitrogen, oxygen, oxygen, non-bonding pair, minus. Okay. It also has that delocalized pi bond that exists simultaneously on either side. Okay. So, looking at it, okay, you get a sort of smeared, pi bond across the entire structure of the molecule there. And that is another delocalized pi bond. Okay. So, just to refresh, you can only get resonance, you can only get delocalization if you have pi bonds. Hybrid orbitals, sigma bonds, are locked down. Pi bonds are free to resonate, free to delocalize. All right. Now, for those of you who are curious, we're not going to be covering Section 4 of Chapter 8. Molecular orbitals are, the real deal. They explain this stuff. They explain geometry and why bonds form and so much more. But they are very complicated. And without symmetry math, I think that molecular orbitals amount to a lot of memorization and not so much understanding. They are great. They're a powerful explanatory tool, but they are just not for us, sad to say. In any event, that does it for this lecture, and that also does it for Chapter 8. I will see you again in Chapter 9.